we've built something called Slack After Dark. And if some of you might be familiar with some of my earlier work when I worked with Databricks called Spark After Dark. So on a play, and especially around Valentine's Day, we decided to implement online predictions and actually online model training with Keras and using Slack. So Ansha built this really cool demo for a company demo for using MapR. So she's going to show that here in a bit. It's not a plug for MapR or anything. It's just to kind of show some of the pipeline stuff and show what you could do with online, more sort of real-time machine learning versus batch machine learning. So that's where she fits in. You can see there's links to community like edition here. Also, Ansha came up with this fun Slack After Dark logo, which I hijacked and added the pipeline logo in there. A couple other things as well besides this goofy Slack After Dark thing. We're also going to, towards the end, talk about how we've improved our PipelineAI JupyterLab like notebook integrations. You could actually deploy models directly from JupyterLab. You can also manage clusters and all the things you would expect and you see from other tools like Databricks and Qubole and Cloudera's Sense.io, things like that. We've also, coming from Databricks, I'm very familiar with the MLflow stack, and I know some of the engineers working on it. This is experiment tracking, so I'll show you how we've integrated that into PipelineAI. And finally, while Ansha is going to be talking about the MapR distributed file system, in an effort to keep things a little bit more open source, I've gone ahead and we've implemented Rook and Ceph as our distributed file system to let us do distributed model training across the cluster using a shared file system. So I'll get to some of that here in a bit. Let me show you guys what Slack After Dark, what's going on here. So the main premise is we're actually matching engineers with non-engineers. The thinking here is opposites attract. This is our theme. We basically needed a matching function, and that was what we went with for the matching algorithm. So upon login, you could do, when you first log in, you give it your picture, and it will actually rate you and say what percentage you are engineer, non-engineer. This is totally, sort of bogus, sort of arbitrary data, but we needed something fun to go with here. So, and I think Ansha's going to do this live, but I'll just kind of show you what is happening here. So when she first logs in, she passes her image. We actually run it through two different algorithms. We are doing an ensemble of version 1, version 2. Version 1 was trained on less data. We use transfer learning here, so we started with MobileNet. We trained it on just a couple images for Model 1, and then Model 2 we actually trained online, and I'm just going to show you how we did that. But sort of once all the training's been done, we can actually make a version 1, version 2 ensemble prediction. And you can see the average prediction is 64 engineer, 36 non-engineer. We think it's probably has to do with her Docker shirt that she's wearing there. And also the max prediction, the maximum prediction was by the better model V2, which we expected, which actually had 93% engineer and about 7% non-engineer. And you can now see the individual prediction. So you see Model 1 was actually not a very good prediction. Model 2 was very good. We decided to ensemble them just because we can. And then here's the exciting conclusion. When Ansha did a /match, she actually got matched with this guy, Erlich Bachman, from the fictitious HBO show Silicon Valley. These are two of my favorite shirts, Docker shirt and I Know HTML. So I think I'm going to hand it over to Ansha. Right, like again, towards the end, I'm going to show you some of the, let me scroll down here real quick to give you a preview. Oh, this is some of the online training here that we're doing through Slack. We actually start it with Slack. You get progress updates. At the very end, we're actually posting the final accuracy results and loss results. And then also, you could deploy models directly from JupyterLab now to Pipeline. And we can actually train 4 different variations of the same model, do hyperparameter tuning with different hyperparameters, batch size, different number of epochs, that kind of thing. You can see a visualization that's powered by MLflow that's now integrated with Pipeline and JupyterLab. Show you too some of the debugging. And lastly, the distributed file system with Rook and Ceph. And this actually lets us run the same job across all nodes within our system. And if you, certainly you could use S3 or Google Cloud Storage, but there's always cases where you still need a distributed file system. Okay, so with that, let's hand it over to Ansha. Can you take the screen share?
Yes, let me see if I can grab it from you. Yes, I'll grab it and share my desktop, and let me know if you're able to see my slides.
Yeah.
Yeah, perfect. Okay, so I already did a quick introduction. Antje Bart, I'm working as a partner engineer at Mapper actually, so integrating partner solutions into our technologies, which is a good fit here. I'm focusing a lot around big data technologies, analytics, and recently around container, Kubernetes, and machine learning as well. Also, when I'm not working full-time for Mapper, I'm also running a local chapter for women in big data here in Düsseldorf, Germany, where I'm based. So yeah, trying to promote the technology and the tech area to attract more ladies and women in the field. All right, let's jump into Slack After Dark, and I still love this this logo here. It brings me back to the 80s. So for this demo, as Chris already pointed out, the objective was basically to show an end-to-end containerized and integrated machine learning workflow, showcasing the online model predictions and also the online model training using our technologies, so PipelineAI, our Mapper data platform, and Slack. And you can actually see on the right here, it includes a big variety of technology. So it's not just those, but really a bunch of like cutting edge stuff we're using here, including the Slack API and some fun with webhooks, etc. So what we did to kind of facilitate the tasks we do want to show in the demo, we created 2 Slack applications. So one, which I call the backend service, is the AI Monkey. And this one helps us really to perform the data ops tasks. So this one helps us to test, train, and deploy the model in the background. Whereas the front-end service, which is the Slack After Dark Slack app, is basically representing the end-user application, in our case, a dating app. So why have we chosen to integrate with PipelineAI here? And this is really coming down to the fact it runs everywhere. So it supports almost every framework. It runs on every hardware, every cloud. We do have a nice dashboard here, which you can figure out yourself and play around with the community edition here, which Chris pointed out to. It helps optimize, generating optimized runtimes for the models. We do have custom targeting rules, a shadow mode available, and we can do percentage-based rollouts to test new features in live production, and really are able to do this continuous model training and pipeline optimization validation that Chris mentioned. So looking at the architecture for the demo, we're starting off with the Slack channel really as our UI, as our interface. So what we do for the online predictions, we're implementing this ensemble, which is also sometimes referred to as a rendezvous architecture. So I do run a predict command passing an image URL, and then it gets routed to one of the models depending on the traffic routing that is set. What we can also do is then do the predict rendezvous, which then queries all of the models that are in production and sends back the prediction with a criteria which we define. So we selected the highest confidence in this case, or an average, and this one gets back to the request to the person sending this predict command. What we're also doing is grabbing the predict statement and putting that into a stream for archiving and for the replay. So kind of implementing the decoy model. And it also deploys as a canary in pipeline, so you can also compare that one to live models later. It's all running containerized, so we can also show like all the integrations and flexibility you have with containerized workflows here. And then the second big thing is really implementing the online model training of streaming data. So again, we're using the Slack API our AI Monkey app, and we can do either step by step. So we provide feedback on a badly trained model and say, no, this image is categorized like wrong, and categorize it better this way. So we provide human feedback to the model. That data is put into a stream, and then the model gets trained live off that streaming data. As a next step, it creates with MLflow the new model experiment and then deploys the new model into production. So for our demo, we can either do like step by step, or just to save time, we have implemented a fix command, which basically runs through the individual steps like in one run, just to make it a little bit smoother and see what's happening here in the background. But this is really what helps us to get from batch to real time in terms of online model training using components as a stream in here. And then finally, you would like to test your application, obviously. So we'll have another check, and Chris kind of already showed the punchline here with a picture. But basically, you log in as a user into the app, and then you get obviously rated and scored with our unique AI-powered matching algorithm. And then you'll see when you run the match command which person you're matched to. All right, let's see the demo. And I'm going to switch here to my Slack channel, and you see I've been playing around here already a little bit. And I do have some notes here, so we can put this in a little bit quicker. So what I'm passing here as a predict is an image, and let's see if it throws up. Yeah, so I'm processing a picture from Sheldon Cooper from The Big Bang Theory. Probably most of you will know. And what it does in the background, and probably, let me see if it worked. So that's the demo goats. Actually, have to restart a little bit here. Probably run into a timeout. So what it actually does, I pass the image and it runs the prediction against a set model. And then what I'll do, we'll see that it runs against the badly trained model, hopefully, when it starts again. And then I provide the fix command where I say, well, there's another better label to that picture, and just improve the model with that data, and then we'll hopefully see that it's running correctly. So what I'm doing here, I'm building basically first step, the model and scoring database. And here we go again. Sometimes there's, because I have the pictures here on my Slack channel, on the GitHub as well, it sometimes runs in a little bit of a timeout. So I'll try this again. I'll do a predict command here, and I pass Sheldon's image. There we go. So we see it got to model 1. So we see a bad prediction. It says like 36% engineer and 63% non-engineer. So what I'm saying here is, well, fix this actually and say this image is basically an engineer. And then what it does here is, and we'll see a couple of steps showing up here, and I just scroll up a little bit to see. So what happens is we're passing my feedback into a stream, which is step 1 from 3 here. And then we do in the background a new model run. So we're training a new model V2 from that streaming data. And we can see here the training results, what Chris also showed earlier in the blog post already. So we see with a new training set, the model gets better and the accuracy goes up. And then we're basically storing the model file data in the distributed file system and deploying the new model. So we can do those from, as Chris mentioned, different locations. And the idea is really not just to be myself in the Slack channel, but maybe your whole company being in the Slack channel, or even having bigger communities training the model data when there's kind of a non very accurate result. And so you can live improve the model. And then we can see here versus model 1 traffic, we now have V1 and V2. And what I can show now is do a predict rendezvous here with that image, and it basically queries now both models, and we see this output here. We have the average prediction, and this is totally customizable. I just said, like, give me an average prediction, give me the maximum, which in this case is the highest confidence level, which is 97% of the model V2 we just deployed and trained, versus the 36% like the first predict replied back. So we see now that both models actually receive traffic. So this is nice. So we want to have some fun with the dating app as well. So what I do here, and by the way, you see that this feedback here is coming back from the AI monkey. So this means that was our data ops tasks in the background to prepare our app. And now I'm switching to the front end actually, and I'm doing a login. And I'm basically grabbing a picture of myself here again, just to see what's happening. I do a login. And basically, it adds my picture to the database, which we're using as a user and scoring database of the app, basically. And it runs my picture through those prediction models. And I got assigned a profile to me, which is 64% engineer. Glad that I'm wearing the Docker shirt here. and now I can do the match command. And this will basically use our highly sophisticated algorithm in the backend and match myself with Erlich from Silicon Valley. And this really shows in action all the steps we just described, like how you can use a simple interface like Slack to integrate with your model deployment workflow, help issuing a couple of those commands, do online training with streams, and really integrating into a whole data platform, having PipelineAI doing all the heavy lifting for you, and then come up with a simple and fun application here to just also make it like a nice way to show to people who might not be like that deep into the machine learning and AI topics. And with that, I hand back to Chris and see if there's any questions.
Cool. Yeah, thanks, Antje. Let's see. Got a couple questions here. One batch update, including the very last data to how do you deploy them? Okay, so yeah, we get this question a lot about how big are the batches of, so just like any machine learning use case, you have to be careful how often you train, what type of data that you're training on. Continuous training isn't always the best thing, depending on what you're trying to do. If you're trying to capture trends, then it's good. You have to make sure though that each night you would do like a larger batch of training to potentially to avoid any overfitting on these sort of intraday trends. One batch update, including the very, okay, what format to use for saving the models? Yeah, so we prefer TensorFlow serving the saved model format. The reason we like TensorFlow is there's a lot of things you can do to your models, your TensorFlow models, after they've been trained, this whole space of post-training optimization, we call it. If you notice, when you go to deploy a model, let me go to the deployments tab here. If I click here, let's see, and I can click here to see how it was trained and any hyperparameters that were used, and also the artifacts. And if I click the play button here, which is deploy, I'm presented with a bunch of options here. I could actually choose to quantize, down from 32-bit down to 16-bit, quantize to 8-bit. I could fuse layers together. I could actually choose 3 different runtimes here because this is a Keras based model with a TensorFlow backend. So the short answer is that we store it in the format that gives us the most flexibility for post-training optimizations, because we could actually generate 3 different variants of the exact same model and push that out and then compare them live in production. So if I did this, if I have CPU and I have Python, TensorFlow Serving, and TensorFlow Lite, I'll actually get 3 different like Docker images and 3 different variations of the exact same model, and they've been post-processed to optimize for these 3 runtimes. And I believe, I don't have it offhand, but there's a picture showing one model we've generated 11 different variations, and we can compare them across all 3 different clouds. And let's see. So, any other question? You've been training the model in real-time online machine learning. Why do you have that in a distributed environment? How do you handle concept drift? Yeah. So, right, like exactly. And keep in mind, Pipeline is a platform that's giving you the capability to do this in real time. So again, sometimes that's not always the best thing that you want to do. So you would have to, we can help you detect the drift, and then you would either retrain or you would somehow adjust. You could even roll back to a previous version. Let's see, how do you do that in a distributed environment? All of this is distributed. So again, the distributed file system, either MapR or we use Ceph and Rook, help you train across all of the nodes in the cluster. That's more of a cluster management, parallel computing question. Also, you can do Spark ML across. We actually have a Spark example. If you click on notebooks over here, we should have a Spark example that you could follow. It's a pretty simple one. It's just doing the classic Pi calculation, but shows you how to do this basically from the command line. We're working hard to actually integrate this and generate the Docker image and then deploy it to the cluster with just one click. Let's see, there's a question I missed. Can PyTorch be used? Yes, of course, PyTorch. And let me show you guys, if you click on samples over here, we actually have a whole bunch of samples. So you can see TensorFlow, Keras, PyTorch, Scikit, XGBoost, Python, Spark, MXNet. We've got, most of these have been implemented, and it's the exact same model. It's the classic MNIST model. So let's call this V1 demo, and it's a PyTorch model. It's MNIST, and that's going to produce a variation here for PyTorch. So it's the same project. We have a Keras model, and hopefully soon we'll see the PyTorch one pop up here. And I can click on this, and I can deploy it. And we automatically detect it's a PyTorch model. There's not as many options for PyTorch models as there are TensorFlow for the runtime capabilities. For the different hyperparameter tuning that we're doing live in production. So just keep that in mind. Most people that we've been talking to actually do PyTorch in the research lab, then they rewrite it in TensorFlow so that they can then fuse the layers and do a bunch of GPU tricks that are given to you by the NVIDIA folks with a custom runtime called TensorRT. That's available for the NVIDIA GPU. So yes, TensorFlow, and actually there's a couple videos online where we compare all of these different samples, or at least the top 2 rows. So we have 8 different implementations across all these 8 different frameworks, including Spark and MXNet of the MNIST model, and we compare them live in production. And yeah, obviously TensorFlow is blazing fast. Keras is using TensorFlow backend, so we can do similar things to the Keras models. Scikit-learn's pretty slow. XGBoost isn't the fastest online, but pretty good training-wise. And yeah, MXNet's pretty fast as well too. Do you support PFA? We support PMML. We actually we don't see a whole lot of PFA, but we're certainly familiar with it. But we follow where the market's taking us. But that is a good suggestion. We have could probably revisit that. PFA is kind of next generation PMML. It's created by the same folks that created PMML. It's a little bit more flexible. It's basically its own little scripting language, and you can define anything pretty much with PFA. I know the IBM guys have done a little bit with PFA, and they have a custom runtime for PFA as well too, so that's something you could certainly look into adding. Is there any way to parallelize code? If you mean training-wise, yes, of course. You would use distributed TensorFlow or distributed Spark. Spark is distributed by nature. Let's see. Pre-processing takes a lot of time. Yeah, so I believe what this person is getting at with this comment about pre-processing taking lots of time, meaning even on your prediction side, when you are predicting with raw data, you need to apply the same transformations that you would during training. And so there's ways to share the same snippets of code. With Pipeline, you could actually define what we call transformers. So there's the input transformer, which gives you the ability to either run a TensorFlow graph or even just a snippet of Python NumPy code where you're reshaping the image or scaling it down or grayscaling it. And then also you can write a transformer on the output. So after the prediction has been made, you could take the NumPy array that comes out of your scikit model or the tensor out of your TensorFlow model. You can transform it into JSON or CSV or whatever the caller is expecting. And that certainly does take a lot of time. We have, as part of the Pipeline platform, when you deploy, we have metrics around all of these different steps. So if you break down a prediction into pre-processing, predicting, and then post-processing, we have timings around all of those. So we don't have dashboards turned on in community because we're actually undergoing sort of refactoring in that area that will be released later this week. And you'll be able to tie together, Riley, basically be able to drill into each model that's been deployed and see the timings across all three of those phases. Can you tell me more what you do with PMML? Yeah, so PMML, again, we use the the Java runtime for that. We use a project that I believe is JPMML. And that's a runtime that can interpret the PMML code itself. So we support Java. We also support Python runtime. We also support native C runtimes, which is where we get a lot of performance, especially TensorFlow serving. Let's see, online and offline training. Okay, so online training versus offline training. So online training, there's actually something called, let's see, and scikit-learn is really probably the most tangible way without talking about neural networks. There's something called partial_fit. That's part of these linear models. And partial_fits. This is a good intro. So when you're fitting models traditionally with scikit-learn, you're calling fit. And that's telling scikit-learn that you have all the data. And with partial fit, you're actually telling scikit that you're only giving it part of the story, right? Only a like mini batch, if you will, of data. And so backing up a bit, when we talk about neural networks, these neural networks are always ready to be trained, and they are designed to be trained on mini batches typically. So the kind of common link here is scikit-learn. This is, for these linear models, are when you could do partial fit. For more complex models, sometimes partial fit doesn't always work. You actually do need all the data. But for linear models, specifically with the SGD, the stochastic gradient descent optimizer, you can provide mini batches. And yes, SGD works very well with that. So backing up and talking about neural networks, the most common way to train a neural network is with stochastic gradient descent. And these things love these small little mini batches of data. So back to the original question, which is what's the difference between online and offline training? Online training, you are pretty much always dealing with just subsets of data. And the one thing you have to be careful of is overfitting to the subset. So typically what you do is you sort of dampen what's currently coming in and try not to treat that as the ground truth, but more just a current trend. So classic use cases would be these news feed things, or back to the Slack after dark where you're clicking around, you're viewing certain people. We didn't implement the swipe left, swipe right part within Slack after dark. That's the next step, kind of fun step. But as you're swiping left and swiping right, similar to Tinder, you would be training the system currently what your preferences are. Maybe you're in the mood for engineers or non-engineers, depending on what's going on that day. So whereas offline training is batch. So sort of offline and batch are synonymous here, and then online and then real time. sort of mini batch is the best way to think of it. So what typically happens is you capture trends throughout the day on the streaming data that's coming in. Or as Antje showed, the ability to fix predictions. So the classic use case is fraud, for example. So throughout the day or throughout the week, people start to learn and defraud the system by uploading images with phone numbers in them, or right, like various other ways to move off of a system like Airbnb and to kind of take the transaction offline or off eBay. And the ability to catch these fraudulent or sort of unconfident predictions. So if the model can't tell if something seems a little bit wonky, but it's not entirely confident, maybe it comes back 51% fraud and 49% not fraud, it will still return the prediction in real time, but in the back end, we've sent off the image to Slack for the entire data science team or the entire company to label and have a human that's in the loop. So, this can scale fairly well. I mean, it's still human scalable and it's human in the loop scalable, but you can employ services like Mechanical Turk by Amazon to get more and more people, and then you could have sort of the quorum, right? If 3 out of 5 people that are fixing this prediction say it's fraud, then we consider it fraud. And so, yeah, all of this goes into the next round of training. And let's see, for this demo, do I need to pre-process my input image, make sure it has the right number of pixels? Yeah, the input would get pre-processed. Right, so as part of the invoke, and I can actually send you some sample code here. So all of these samples are in 2 places, either notebooks, so I'll paste in here, or in models. Those are the samples. Let me get sample notebook I just put together. Oh, actually, let's see. Let me get you the invoke. So this is actually the invoke, and if you notice, one of the steps here is transform the request. So here you see where we're loading the image, we're converting it to grayscale, we're sizing it to 2828. Fortunately, TensorFlow does have quite a bit of image manipulation, like utility functions, because a lot of what you do with these neural networks and convolutional neural networks is sort of the image recognition, object detection. We're training heavily with images. So similar to the NLP side of things, where there's a lot of utilities to create word embeddings from documents and compare like document similarity utilities. These are the 2 big neural network use cases, is text and then images. So there's a lot of this stuff that's built in, so we're just reusing it. And the cool thing is you will get automatic timings across the transform request and transform response. So this is a pretty simple response where we know, so this is actually MNIST here, that the different classes are 0 through 9, and then we have the probabilities that come out of the, and we convert it to JSON and then return it back to the caller as a quick little unit test down there. So yes, the larger problem here is that whenever you're doing predictions, you have to know the format of the input data that was used for training. And this is actually something that you can detect if you start to detect variances, not just in sizes, because like you could resize pretty easily, but if there starts to be variances in the distribution of inputs that are coming in, if your model has been trained on a different distribution, then potentially your model isn't the best model at that time. So this is part of what someone called concept drift earlier in the chat, which is the ability to start to detect when this model is no longer relevant. And this is very, very common for fraud use cases because people are always doing different things to defraud the system. Question here is, what do you do with Onyx? Yeah, so Onyx is to us just one more runtime. It would be like, yes, I always joke that Onyx is PMML, but 30 years later. So Onyx is a common format, and we certainly support it. I believe it's listed here on, on the samples list. So with Onyx, we use the MXNet runtime for this, and we get pretty good performance. We actually don't see too much Onyx. This could be because we're commonly associated with TensorFlow and that community and the Scikit community, but not necessarily on the MXNet community. But yeah, all of these, I believe CNTK, Microsoft CNTK is being deprecated or being sort of downsized a little bit, but we do see quite a bit of Java native, PMML, lots of XGBoost. In terms of boosted trees, TensorFlow does have a pretty good boosted tree, the implementation that they claim rivals the performance of XGBoost, particularly on the inference side. So you might want to try that out. We've seen quite a few customers go from their XGBoost models to TensorFlow, the boosted trees, specifically to get the benefits of the runtime. Because, yes, otherwise XGBoost, well, there's a C runtime for XGBoost, which is the one that we prefer, which is pretty good performance. File format for externalize the model have fields specifying the input size should be. Yeah, so certain, when we export TensorFlow models, for example, there's a way to do, I can show you guys actually a notebook here. There's a way to do, there's a CLI, or you could actually call a Python function that will describe. So if we take this sample here, let's run through, and I've got dark mode turned on here within JupyterLab. So this is JupyterLab, and you can change into dark mode here by going to settings, change to JupyterLab dark mode. Okay, so here we've trained a model. This is a TensorFlow model before it's been optimized for production. Let's go to export. So now we're actually going to export this model, and I'm going to show you guys a little CLI command here that you can run that will, so here's a saved model. And there's the save model CLI that TensorFlow offers, and there's a Python version of this as well too, I believe, but when I built this particular notebook, there was only the CLI. But this is going to dump out the schema of the inputs that are expected. So you can see signature def here. Let me zoom in a little bit. It's expecting, see, this looks like it's a list. Oh, because this particular model is actually linear regression. So all it's expecting is a single float, and it's going to return a single float. If you run the same thing on a more complex model, you'll see lists of things going in and lists of things coming out. So that's a quick way to take a look. If someone hands you a model, yeah, that's the ability to crack it open. You could also, like I showed back here, there's ways to dump out the model. This isn't really showing a schema as much. You can kind of infer it, but yeah, there's a couple different ways to inspect models that you've been given. Yeah, so great questions. Let's see. SparkML, oh, I missed one here. SparkML is batch training, so you retrain the model in batch and apply it in streaming. How does the model adapt in real time? Yeah, so looks like this question only got asked to the panelists. Let me restate it here to everybody. So yes, SparkML is batch training, and that's by design. The ability to parallelize and distribute across the cluster is very, very powerful. The way you would do it with SparkML is you would essentially do like discrete continuous is the term that we use, which is every hour you're training the new model off of Spark streaming and either combining it with the model that's already been trained, like depending on how long it would take to actually retrain the entire model with the new data. Depending on the types of models, like SparkML, really only the linear models can be trained off of a stream. Yes, otherwise, the way that the math works on some of the more complex models is you can't just provide incremental. You actually do need the whole batch. These neural networks by design can be incrementally trained. And again, with scikit-learn, you'll see partial underscore fit. This is specifically on the SGD classifier, but there's lots of other linear models that support partial underscore fit that can be trained on partial data. So it's a part of scikit-learn not many people know about. They're familiar with how to fit a model that requires all the data, but you could actually do partial underscore fit. Generates glue code for Python or C. Yeah, that's a really good question, and I had a feeling that you were leading towards that, Yefim. The question here, oh, okay, so Yefim's questions aren't going to the whole group, so let me post that here. And he also, okay, so those two questions. Yeah, as far as I know, there is not any tool that can inspect the schema. Funny enough, I was just working on that over the weekend. We scheduled in for the next few weeks. When you upload a TensorFlow model, it'll actually show you the schema. That's kind of the first step. And code generation for us, or on the invoke side, is we do partial code generation, but it's more stubbing out. But the next level is to actually inspect that TensorFlow model and then stub it out with specifics that do map to that schema for both the input and the output. And also the other thing that you're probably getting at is there a way to like validate with that schema? So if there is input that comes in, can we right at the front door like reject that like input coming in and say this doesn't follow the schema? That sort of opens up the floodgates towards very, very tightly controlled like inputs and outputs, and it's not something we've seen a whole lot of people ask for. Usually you're working with the data scientists to figure out that schema, and if it changes, you then have to go change your prediction code as well too. So still like a bit of manual work there, but yeah, great questions. This is very, very error prone, and also it's not just error prone, which is actually, that's easy to detect because you can right away tell, but there's performance problems here too. So if the schema is too broad, or maybe there's something that can be done on the client device that's calling into this service, you might actually want to push back some of these transformations somewhere else, because you could find yourself in a case where you're the most recent example, and we've seen this actually multiple times, where people are trying to do these complex pandas conversions in the invoke method, which is meant to like happen in tens of milliseconds, if not smaller, and they're using batch libraries like pandas to do these more complex transformations on the request response. So yeah, like definitely something to keep an eye on, which is why we have these dashboards that we're going to re-release here in the next couple days to actually highlight where we're spending time in these predictions. Because not always, the sort of misconception is that it's the model that's taking most of the time, when really we've seen the opposite. We've seen where the model is as fast as it can be because of either Spark ML is able to like create the most optimal like model transformer, or like TensorFlow is able to like rearrange things to make the like that prediction happen quickly. But people, when they're writing their own code, their own Python code or their own Java code to transform, yeah, they tend to do things in kind of the most human grokkable way, which isn't always the most compute efficient way. Let's see, somebody else asked. Deployed on edge. Yeah, so can the models be deployed on edge devices like Raspberry Pi? Yeah, we don't have this natively built in because we are more data center sort of cloud focused, but especially with models with TensorFlow Lite specifically, so that's one of our deployment targets, is we could post-process and transform your TensorFlow model into TensorFlow Lite, which does work across some of these smaller devices. Yeah, so Raspberry Pi does have a TensorFlow runtime, which is pretty nifty. And but yes, we've seen some people do that. It's not like one of our deployment targets. So if I take a look at our current deployment targets, it'd be cloud, on-prem. This used to actually have Amazon, Google, and like Azure. We don't see too much hybrid cloud deployments, but typically people have a single cloud that they deploy to, and then also on-prem. Oh yeah, yeah. So someone's asking about the meetup and me as organizer. The short of it is meetup.com. Let's see. Yeah, how do I explain it? The payment expiration thing came up, and I thought it was all worked out with meetup.com, but they sent out a big email. The short of it is I'm still the organizer. I just had to quickly go back and make the payment in a different way. So I'm still the organizer. Just required some meetup.com customer service. Okay, great questions. Yeah, Ansha, do you have anything else to say? Anything that you thought of?
No, I think we had a good round of questions here.
So do you enable integration with business rules execution engines? Yeah, we have. So our most common integration obviously is through the REST or the gRPC interface. So any rules engine that can execute and call into REST, and then essentially it's bound by all the same SLAs that a typical web request would incur. And then also we integrate, of course, with Jenkins, so the ability to deploy models directly from Jenkins. We have a CLI. If you go to quickstart.pipeline.ai, and specifically we have a Kubernetes Quickstart. And this, we've been working with quite a few people. They've been deploying to EKS, which is the Amazon Kubernetes Managed Service. Also, we just heard back from someone who's installed this on GKE, Google's Kubernetes engine. So if you go to that, and all these quick starts, if you just go to quickstart.pipeline, you can look at the Docker one, you can look at Kubernetes, there's a community. So this is how you would train the model locally. We have instructions how to clone the model, or that models repo. So for the future, for the next month, when we meet again, we'll be talking about tighter Airflow integration. We'll be talking about more MLflow integration, of course, more Jupyter integration. And what else? We've got more samples. I do want to and then better Spark integration. That's the big one between now and next month. So we'll be able to actually right-click on a notebook and deploy it into a Docker container, which then gets distributed across the cluster. And then essentially we've completely matched the Databricks functionality. So pretty excited about that. You could select a notebook, and yeah. So we'll basically be taking this notebook and then automating it so that you don't have to know what the Kubernetes API server is. You don't have to specify any wonky Docker images. These are samples here. This will all be generated for you. I do want to highlight the privacy. So differential privacy is something that we've been focusing on quite a bit. So Pipeline is focused on balancing accuracy with latency with privacy, and the ability to experiment quickly and figure out which hyperparameters, both offline and online, help you achieve a nice balance between accuracy, latency, and privacy. So there's some pretty cool things. There's not a whole lot on the internet and even YouTube or podcasts about differential privacy. Apple highlighted differential privacy, that's the term to search for, during one of their recent WWDC or WDC, whatever it is, the Big Apple Developer Conference. They didn't give too many details about how they're using differential privacy, but they do mention that that's the approach that they take. So it's essentially introducing noise. And so when you train with noise, you can subtract subtract out that noise if there's enough data when you go to make the prediction. You could actually, and so when you train with noise, that's preventing you from being able to get to an individual piece of data, of training data. So that way, even if you do take your one single data set and go through and pull out all of the private sensitive data, that way you can still rather consider your model to be or have the guarantee of differential privacy, which is, and there's different ways or there's different degrees of this guarantee. This could either be very, very private, but you suffer accuracy, or it could be sort of medium private, and then you have decent accuracy, decent latency. The other one to highlight here would be, we've got this hyperparameter tuning like notebook that we built last night that shows the Keras model, the same one that Antje is using with transfer learning. Oh, actually, yes, I apologize. This is actually the MNIST model here. And we've got the MLflow logger. So this, as part of Keras, you can define loggers. So as the training is happening, and that's actually how we achieve this thing here when you do /train, and then it shows you. So this is, there's an MLflow logger, but then we've also implemented the Slack logger, which posts to Slack. And of course, there's really not much code there except the security token and the channel name. But this is making callbacks to Slack as the training is happening. When the training is complete, it then posts this nice image, which is pretty slick. So, kind of a fun thing to do. You could kick off a training job and then, go to lunch and keep an eye on the training from your Slack app on your phone. But this one's actually, you could run, so down here, if I run this here, we'll generate. So here I'm giving it a list of epochs, just 2 and 5 for right now, and then batch sizes, 64, 128. And this is going to cycle through and do all the combinations. So, this is a basic hyperparameter, sort of grid search way of finding the best hyperparameters. These are all getting logged into MLflow, which we'll see here in a sec. So here it's actually dumping out using these callbacks we're generating. So that was, I believe, with 2 epochs and 64 batch size. Now this next one is 2 epochs with 128 batch size. Yeah, just a reminder, epoch is one complete pass through the data set. And I think it's going to do 2 more here. So 5 epochs, 64. And so all this is getting logged to MLflow, so which is our experiments tab here. Let's go find it. It's probably the very last one. All the way to the bottom. So here's, actually, let me see if it's written it yet. Maybe it hasn't. I think once this is done, it'll post them all to, let's give it another sec here. It's going to do one more round. But yeah, you would click on experiments, and then from there, you could deploy these models and manage them. We also, of course, have stream support here, some light Kafka. You can add a topic. You could subscribe to topics from your notebooks or from Airflow. As workflows right now is just the Airflow app that's running on Kubernetes and using the same shared file system that we use for the notebooks, MLflow, and all of our deployments. So I think that's it. Let me see if this is finished yet. Exciting conclusion. Okay, experiment is called this, V1. Oh, okay, so I was on the wrong experiments. Let me go back to our experiments. I probably have a bunch of these, so let me go to the last one. Hit refresh. We should see all 4 runs in very bottom here. Let's call v1. Hang on. Yeah, so here we go. So this is the experiment that we just ran, and it has, we can compare these. Whoops, I clicked too much. And from the command line, you could actually use Pipeline as the remote tracker for MLflow. So you would actually give it, and there's an example in the models, which I can point out here in a sec, but here, let's compare these. Here it's showing the accuracies. Let's hit compare. And some simple plotting. I think the plotting actually has some pretty cool features. You could scale in, scale out. You could look at validation accuracy, plot that. So some pretty basic stuff here, but pretty powerful. If you're familiar with the project called ModelDB, that's very similar to MLflow. And yes, MLflow is kind of a modern version that supports both the newer versions of Scikit and TensorFlow and Keras. So the other thing, so yeah, Ancha already showed more of the Slack integration, and I think that's it. Let me check here. I was going to show you guys the models. Example. So models, Keras. There should be one called MLflow. I think it's MLflow MNIST, pipeline train. And you can see here, so this is the callback including the Slack and also has the tracking URI. So let me show you guys two things here. And then we're going to wrap it up. Boom, boom. So this is the Slack. The Slack logger. And this is the setting the tracking URI to pipeline. Okay, and I think I have to get going here, so I'll try to answer Yefim's questions here offline. And I appreciate your time. Thanks, everyone. Thanks, Ancha.
Thanks all. Bye-bye.
Bye-bye.